So when we're looking at Vesper three-dimensional shapes, the most important thing to pay attention to is the central molecule. The basic type of Vesper shape we'll see is if there's only two atoms, we don't really have a central molecule. These ones will always be a linear structure. So the two atoms are going to try to space apart as far as they can from each other, which will be 180 degrees. The electrons will repel and they'll spread out. The farthest distance that they can make from each other is an angle of 180 degrees. Next, we're looking at something that has more than two atoms. Again, we're always looking at the central atom. Okay, it doesn't matter what's attached to it, it only matters what's in the middle of the molecule. That will determine the Vesper shape. The rule for Vesper when it comes to double and triple bonding is we count them as a single bond. So something like this, CO2. If I were to create the Vesper shape for this, carbon would be my central molecule, and then I've got two oxygens. The double bonds act like a single bond. So in this case, I also have a linear structure. And we would call this linear, you could call it a triatomic, because we do have three atoms as opposed to only two here. This would be a diatomic. And if you check on the chart on page 95, our central molecule here has 0 lone pair, and double bonds count as single, so it has 2 bond. Okay, that matches up with a linear molecule. So you can always check this table on page 95 of your textbook when you're first starting out drawing these. Next one, we look at BCl3. So my central atom is a boron, and it's got 0 lone pair and 3 bond. So if we check the table on page 95, this is going to give us a trigonal planar. Okay, and if we look at the shape of that, boron would be our central atom, the purple, and then we've got 3 single bonds attached to it. No lone pairs around the boron. So what it means by trigonal planar is if we kind of look at this from a side view, all of these lie in the same plane. It's flat. If you were to set it on a tabletop, it wouldn't be sticking up, it would lie flat on there. There's no lone pairs repelling, so the 3 are going to spread out at about 120 degree angle each. That's the farthest distance that they can create between the electrons. Next we have a methane, Ch4. If we look at our carbon, our central atom, we have 0 lone pair and 4 bonding. So again, check the chart on page 95. This is going to give us a tetrahedral shape. And what that's going to look like is if we stick, so if this is our carbon, this time we've got 4. Now we've got the bottom is kind of like a pyramid shape, and then we've got this top atom up here. 3 of these are going to lie in the same plane. So this one, and this one are all lying in the same plane. This one back here is kind of sticking out behind. This one is sort of popping out of the screen. If we were to draw the Vesper shape for a tetrahedral, you indicate this by using dotted or solid lines. So the one that's sticking out would be like a thicker solid line, and the one that's kind of in the background we show with a dotted line. Okay, the last type of shape is NH3. In this case, our central molecule is nitrogen. We've got 1 lone pair and 3 bonds. So look at your chart on page 95. This gives us a trigonal pyramidal. So this is the second shape we have where we see that word trigonal. Difference is planar, this is lying flat. It's all in the same plane. Pyramidal is more of a 3-dimensional shape. So a trigonal pyramidal is actually just like the base of a tetrahedral. Lone pairs and bond pairs repel each other just the same way. So if I take off one of these bonds, but I add a lone pair, and then we kind of rotate this so the lone pair is at the top of the molecule, you can see that it looks almost just like a tetrahedral. So where that fourth carbon was on the methane that we saw, here's the lone pair. If it was no lone pair, we'd have a trigonal planar. Everything would be lying in the same plane. When we add that lone pair, it kind of repels and pushes everything down, so we've got this pyramid shape now. And we would draw it just like we would with the tetrahedral, except you don't include that molecule on the top. So you draw it the same way you would draw a base of a tetrahedral, which would look like this. Okay, the very last type we'll see, which is common that students will mistake this for linear. I'm going to use water as an example. Water is H2O, so this would be the oxygen, these would be the two hydrogens. Except we have to remember that oxygen has two lone pairs attached to it. We don't get a linear shape here. These lone pairs are going to repel, and it actually causes it to bend down. So without those lone pairs, we would have a linear molecule. With them, it causes it to bend, and we get angular or V-shaped. On the lab